Okay, so I'm going to go ahead and get started. My name is Terrence Kelly. I'm here to talk about practicing the persistent memory style of programming on conventional hardware. So a note on terminology. Sometimes the words non-volatile memory and persistent memory are used synonymously, but I'm going to try to be careful to use those words in the following way. When I'm talking about a novel kind of memory hardware technology that retains data even in the absence of continuously supplied power, I'm going to say non-volatile memory. When I'm talking about a purely software abstraction of memory that sticks around longer than the process that manipulates it, I'm going to use the term persistent memory. Okay, that'll hopefully become clear as the time goes on. Okay, so this is a long talk, and if your attention span is shorter, I invite you to take a picture of this slide, come back to it when you get bored. You're invited to participate in a 5-minute mini-hackathon that works like this. In the current issue of ACMQ magazine, there's an article with the same title as this talk by me that tells you how to get a library called FAMUS, F-A-M-U-S. Get that. The first example program is a C shell script. Run it on a Linux box. It only runs on Linux. Email me the output. I'm going to award prizes to the first 3 correct outputs that I get. Okay, so we're here to celebrate the return of non-volatile memory hardware after 40 or 50 years without it. And this is really exciting. Why? Because non-volatile memory naturally invites a style of programming in which applications leave their data in memory only, and they manipulate data with CPU instructions like loads and stores. There's no external separate persistent store off to the side like a relational database or a key value store. The main attraction, in my view, of the NVM style of programming is simplicity. It allows us to get rid of big, complex, opaque moving parts. There's no external persistent store with its own rules, its own idiosyncrasies. There's only one format for data, the in-memory format. No more serializers, parsers, or other translators. Programmers only think in one programming paradigm, imperative algorithms manipulating in-memory data structures. The programmer doesn't have to mentally context switch to some other paradigm like declarative SQL, manipulating data in relational tables. All by itself, simplicity can reduce the cost of software development, make it easier to write correct software, and offer performance improvements over and above those that you get from new, faster hardware. Several NVM programming frameworks or platforms have been proposed. I've listed a couple here from academia and from industry. These differ in several ways. For instance, in the extent to which they leverage compiler support, in the steps that programmers take to ensure isolation in multi-threaded software. But the main difference among them is in their crash consistency mechanisms. On the other hand, all of the platforms and frameworks that I'm showing have a couple of things in common. They all assume that the developer is writing software in C or C++, and they all assume that the application lays out its data structures in memory mapped files. Okay? So in order to focus our attention on a similarity, we're going to temporarily ignore the major difference. We're going to assume for a little while that failures simply don't happen. Forget about crashes. What's left is the major similarity. Applications laying out data structures in memory mapped files. When you think about it, you realize, well, I mean, do we need new hardware to do that? Do we need non-volatile memory for that? Haven't we been able to do that for a long time? Indeed, we have. If you take a handful of techniques and idioms and tricks and connect the dots, you realize that it has long been possible to practice what I will call the persistent memory style of programming on conventional hardware. Ordinary volatile DRAM and block address storage. How does it work? Well, the application lays out its data structures in memory mapped files. Typically, the backing files containing persistent data are going to begin life as sparse files because logically enormous but zero footprint sparse files, because that gives us a nice pay-as-you-go resource footprint. We're going to use pointer casts on the return value of mmap to interpret the contents of the memory mapped files as typed application data. Almost always we're going to want to layer a persistent heap abstraction on top of raw persistent memory, a persistent allocator that simply allocates memory from a memory mapped file. And as we'll see, it can be remarkably easy to slide a persistent heap underneath complex legacy software that was never intended to be persistent. All of these tricks and techniques and idioms have always been implementable on conventional hardware. You don't need non-volatile memory to do any of this. So in some sense, the purely software abstraction of persistent memory occupies a fourth category of knowledge overlooked by the great philosopher Rumsfeld. It's something we know, but we don't know that we know it. The first part of this talk is just us reminding ourselves that we have long been able to practice persistent memory programming on conventional hardware. And for simplicity, in the first part of this talk, we're going to completely ignore the possibility of failures, right? Nothing ever goes wrong. Applications always enjoy a leisurely and orderly shutdown. In part 2 of the talk, we're going to get real again, come back to the topic of how to tolerate failures like power failures and so on, okay? Just as a reminder for those of us who don't use it every day, mmap is a standardized system call that creates a correspondence between byte offsets in a file called the backing file and a range of virtual addresses in a process address space called the in-memory image of the backing file. Those are terms I'm going to use repeatedly. Okay? Once mmap has established this correspondence for us, it's possible for applications to manipulate persistent data in the backing file with load and store instructions. As a warm-up exercise, just to remind ourselves of the details of how it operates, we're going to write a simple C program that performs an in-place string substitution on persistent data in a file. We're going to look for every occurrence of the lowercase string ABC and replace it with uppercase ABC, okay? So we're using a pointer cast on the return value of mmap to interpret the in-memory image of the backing file as just an array of bytes. This is trivial. Once we've done that, we can access persistent data just by walking through it with a pointer and read it via loads, update it via stores. Now it's instructive to compare this simple C program with an even simpler one-liner from the command line. You could use the sed utility to perform the same string substitution. It turns out that the C program can be far more efficient. When you think about it, both the sed command and this little C program must read every byte of their input. There's no getting around that. But the sed program writes as many bytes as it reads, whereas this little C program only writes to the backing file those pages of the in-memory image that have been modified. In the limiting case, the string lowercase abc simply does not occur in the input, so nothing gets written. Okay? Persistent memory programming can be more efficient than obvious alternatives. Now, applications typically want to define their own data types, and they want type-checked access to it. That's not a problem either. Here we have an application-defined data type. When we memory map persistent data into our address space, we use a pointer cast on the return value of mmap to interpret the contents of the backing file as an instance of the application-defined type. This again allows us to access persistent data with loads and stores, but this time we get more interesting type checking. Okay? Now, most applications want to dynamically allocate memory, and in this slide and the next two, we're going to talk about an ultra-simple memory allocator, very simple, very rudimentary, and we're going to see how we can use it to retrofit persistence onto a complex data structure and corresponding algorithm that were never intended to be persistent. Okay? There's not going to be a quiz at this at the end. You don't have to worry about the details. I'm going to briefly go through the highlights of what's going on here. So at the very top, we define a header structure that will occupy the first 4 machine words of the backing file. Okay? The very first machine word is the address at which the backing file has to be mapped into memory. We're going to insist that the persistent heap that we're going to put in the backing file after this header always gets mapped into the same range of addresses in virtual memory every time we use it. Okay, the rest of the header is some persistent heap bookkeeping information.
It really assumes your pointer size is the same.
I could burn a hole through the back of your head with this pointer. Right, so to cut to the chase, several slides in the future I talk about the fact that if things like the endianness of your integers or the size of your pointers changes, somebody's got to write some manual reformatting code. Good point, Christoph. All right, another thing that you find in the header is a root pointer. Now, it's the responsibility of the users of this persistent heap to ensure that all live persistent data is reachable from the root. We'll see in a moment how we use this root pointer, okay? Next, after the header, we've got functions m and f, which are cheap replacements for malloc and free. The allocator is a bump pointer allocator, simplest kind of allocator I know. It doesn't support recycling freed memory, and not surprisingly, free is a no-op, it just leaks. This is C++ code, and down at the bottom, in a handful of lines of code, we overload global operators new and delete to tell C++, now hear this, do not allocate dynamic memory using the conventional heap, use mymalloc and myfree to allocate dynamic memory, okay? Now, a couple of lines of preliminaries here. Now, when our program begins life, it must map the backing file into its address space. It's going to try first to get the address at which to map from the file itself. If the backing file is newborn, it's just a bunch of zeros. So it's going to find, our program here is going to find a null pointer, and it has to use a voodoo heuristic to figure out a reasonable range of addresses in which to map the backing file. Thereafter, every subsequent time we use the backing file, we're going to map it at that very same address. Okay? Now, we perform the mmap call. If we're dealing with a backing file that is newborn, we have to do some initialization work. Okay, we have to initialize the persistent heap bookkeeping information. We have to allocate on the persistent heap a new C++ STL map. Otherwise, if we're not initializing the persistent heap for the first time, we just use the root pointer to find an entry point into the persistent STL map. The point of this code is to take an ordinary C++ standard template library container, a map, and make it a persistent container. So after a few dozen lines of preliminaries, we're done. And we've got a persistent C++ STL map, and we can use it exactly the same way we would use an ordinary map. This is a simple bit of code that reads words from standard input and stores them in the map associated with a count of how many times we've seen each. If you feed in the special word dump in square brackets, it's going to dump all the words that it's ever seen and their frequency counts in alphabetical order. Okay, so the claim is we've taken a STL map and made it persistent. Is it really persistent? Here are some command lines to find out whether that's true or not. We're going to use a command line utility truncate to create a backing file that is initially a sparse file. Logically, it's just a bunch of zeros. Its size is a multiple of the system page size. It's 4K. It's usually convenient to do that. We're going to activate our example program the first time, direct its attention to the backing file on the command line, and spit a couple of words into it. Foo, bar, then we're going to tell it to dump its contents. And lo and behold, it remembers the words that it has just seen. No big deal. That's not impressive. Now our program exits, and we invoke it a second time, again directing its attention to the backing file that now contains a persistent heap that contains an STL map. We feed it one word that it's seen before, foo, one new word, quux, tell it to dump its contents, and we see that it remembers the word bar, which it saw the last time. It knows that it's seen the word foo once this time, once the last time, and it remembers the word quux, which is it has just now seen. So yes, indeed, the STL map is persistent. There are two examples of the program that I just showed you floating around out there. One of them is in the current issue of ACMQ magazine. It offers no crash resilience, and it should run on any Unix-like operating system. The other is bundled as an example with a library called FAMUS, F-A-M-U-S, that is a crash-resilient variant of this code. It's only going to run on Linux. So if you like crash resilience, go for one example. If you don't, go for the other. Now, a fundamental decision that you have to make when you're designing persistent data structures is, are they going to be relocatable, or are you going, as in the previous example, to insist that your persistent data is always mapped at the same virtual address range every time? Well, if you use fixed, non-relocatable persistent data, that offers some advantages. It allows you to use ordinary conventional absolute address pointers, which are familiar and convenient, which in turn makes it easy to retrofit persistence onto complex legacy software that uses pointers, like the STL map we just saw. The downside is that mapping data at the same address range every time, there's no standard portable way to do that that's guaranteed to work. There are heuristics that always work in practice, but there's no law out there that says next week a linker can't put libc.so in the address range that you wanted to map your fixed persistent heap from last week. Okay? More importantly, fixed fixed address data structures make it difficult to share data between independently developed applications. If I've created, say, a persistent heap that must be mapped at a particular address range, and you've created a persistent heap that must be mapped at a particular address range, if those two ranges overlap, then there's no way for a single process to use your persistent heap and mine at the same time, okay? So this makes it harder to share data across independently developed applications. My advice is that you should consider using fixed, non-relocatable data structures if your persistent data is private to a process in the same sense that a conventional heap is, or if you need to leverage existing pointer-based code as in the STL map. Now, on the other hand, if you decide to make your persistent data structures relocatable, that makes it easy to share persistent data among independently developed applications, and there's no reliance on non-portable voodoo heuristics, but the downside is you're going to be programming not with conventional pointers, but with something more like an offset, which is less convenient and less natural. The biggest downside is that you lose compatibility with the large volume of valuable existing code that expects pointers. So my recommendation is to prefer relocatable data structures if you're designing persistent data that is more like a database than a heap. It's intended to be shared among independently developed applications. Okay? So the biggest source of trouble in persistent memory programming is bugs due to mismatches between the lifetimes of different kinds of memory. If you have a pointer or some other kind of reference from persistent memory to ordinary volatile or ephemeral memory, that's usually a bug unless you're doing it deliberately and you know what you're doing. You need to keep in mind that static external global variables are no longer the most long-lived kind of memory in your program. There's something that lasts even longer now. Also, you have to keep in mind that C++ sometimes stashes invisible function pointers inside your objects. You need to know when that's happening and make sure it doesn't cause trouble for you. Okay? Some rules remain the same. Data races have always been illegal according to programming language standards, according to POSIX. Now, a special case of that rule that you need to keep in mind is that if you decide to call msync to flush the modified pages of your in-memory image down to the backing file, there had better not be any threads modifying the in-memory image while you're doing that, because that would be a data race. Okay? If you're writing multi-threaded software, that's a complicated topic on its own, and the intersection of multi-threading and persistence is a very complex topic. We're not going to cover it, but I'm going to highlight a few issues that you need to keep in mind. If you're using something like locks to protect persistent data, if you're embedding locks in persistent data structures, you need to make sure that you need to be aware if the implementation of those synchronization primitives contains internally pointers to ephemeral memory, to ordinary memory. When you think about it, when your program shuts down, we're assuming that it's going to shut down in an orderly way for now. When your program shuts down, it's no longer modifying persistent memory, so there shouldn't be any locks in a locked state, okay, at shutdown time. So when your program wakes up again, there should never be a need to unlock any lock-like things that are embedded in your persistent data. However, depending on the details of the synchronization primitives you're using, reinitialization of those primitives might be necessary. Okay, so the persistent memory style of programming, as we may practice it on conventional hardware, is, as I've shown, a simple composition of tricks that are individually well known, but this collection of techniques as the persistent memory style of programming is not widely taught. The only undergraduate courses that I've ever seen anything like this in are those where I have approached the professor and said, hey man, you ought to teach this to your students. Systems programming books and operating system textbooks, documentation for developers like man pages, doesn't tell you, oh, by the way, you can do this. I think that's got to change. I think we need education for students and for working software developers that teaches the persistent memory style of programming. Its main attraction, in my view, or one of its main attractions, is simplicity. It allows you to write much simpler code. It makes life easier on the programmer. I think that education should include techniques that are implementable on conventional hardware, because not everybody has non-volatile memory, at least not yet. There are lots of computers out there that don't and won't have byte-addressable non-volatile memory hardware. The right approach to teaching, I think, is to decouple the style of programming, the persistent memory style of programming, from any particular crash consistency mechanism. The one thing that all NVM programming platforms and frameworks agree upon is that applications have to lay out their data structures in memory mapped files. Okay, let's teach developers how to do that. There are plenty of developers who don't know, right? Furthermore, the style of programming that you practice, if you're just laying out your data structures in memory map files and you forget about failures, well, that sets the ergonomic gold standard against which any particular crash consistency mechanism can be judged. How much extra fuss do you have to go through to add crash consistency to a non-crash consistent persistent memory program? Okay? So the kind of curriculum sequence that I have in mind goes something like this. We currently teach kids first how to write slow code that doesn't manipulate persistent data. That's bubble sort. Then we teach them how to write fast code that doesn't manipulate persistent data. That's quick sort. Then we sometimes add persistence alone. How do you read and write files, but without any crash consistency mechanism? After that, we can teach crash consistency mechanisms. The interesting thing about going through this sequence is that between every pair of points, the amount of extra code that you write quantifies the amount of trouble the programmer has to go through to achieve a qualitative improvement. Okay, now, we're going to stop suspending disbelief, return to reality, and talk about how we deal with failures, how we deal with implementing crash consistency for persistent memory programs running on conventional hardware. What kind of failures are we concerned about? Well, things like power outages, operating system crashes, application process crashes. If you're just using conventional mmap and msync, you've got a problem because those standard mechanisms offer no data integrity guarantees for your backing file. One problem is that the operating system can write modified pages of the in-memory image down to the backing file whenever it wants in any order. Another problem is that even if you call msync, the operation of msync is not atomic with respect to failure. So after a crash, the state of the backing file is unknown, and it's not a reliable starting point for recovery. I think it's something of a scandal that Unix-like operating systems and the POSIX standard and so forth don't offer any simple, standardized, efficient mechanism whereby applications can failure atomically update application data in files. We should have had something like that for decades. Now, it's true that file systems go to great lengths to protect the integrity of their own metadata from crashes, but they offer no such protection for user data in files. It's kind of like a police department whose only goal is to protect cops from getting mugged. That's a fine goal, but it should not be the only goal. As it is left as an exercise to the developer to implement atomicity mechanisms, which the developer really wants, from the ordering primitives that are supplied, things like fsync and msync. If developers weren't such wusses, they would riot. So a few years ago, my colleagues and I decided to do something about this, and we began work on a mechanism called failure atomic msync. It is exactly what the name implies. It's a semantic strengthening of standard msync, and it gives you a simple guarantee. The backing file is always in a state reflecting the most recent successful msync call, even if something goes wrong, even if a crash occurs. All we're doing is restricting the behavior of conventional mmap and msync. We're not adding new behaviors. We're taking away old behaviors that nobody in their right mind would ever want. Failure atomic msync can be implemented efficiently in the same sense that ordinary mmap is efficient. The only thing that ever gets written to durable storage are modified pages of the in-memory image, and failure atomic msync allows us to tolerate fail-stop failures like power outages, kernel panics, application process crashes. Now, bugs that directly corrupt, bugs in hardware or software that directly corrupt the backing file are not tolerated. And failure atomic msync doesn't fix your C bugs. It's not magic. But as we'll see, it offers applications a well-defined point where they can check the integrity of their data before making it persistent. Okay? So if you're writing code in the persistent memory style using failure atomic msync for crash consistency, you have to follow all the rules that you had to follow when you were using conventional mmap and msync. If you're using some sort of lock-like mechanism to protect persistent memory, when you call failure atomic msync, those locks protecting persistent memory had better be unlocked, otherwise you've probably got a bug, because the same rule applies as before. During an msync call, no thread may be modifying the in-memory image. That would be erase. So upon post-crash recovery, you should never find embedded in persistent data any mutexes that are locked. The most important rule is that you only call failure atomic msync when your data are consistent. That is to say, when application level invariants hold. Right before you call failure atomic msync, that's a great time to check those invariants as thoroughly as you can afford. If you do that, you can crash with confidence in your program anytime, because a crash in your program will never corrupt the backing file where your persistent data ultimately lives. The simple example of transferring money from one bank balance to another illustrates when you can call failure atomic msync and when you can't. So if after you've decremented one bank balance, but before you've incremented the next, it is a bug to call failure atomic msync, because we've disrupted the conservation of money invariant, but not yet restored it, so a crash can destroy money. Now, on the other hand, after you've restored the invariant, then it is correct to call failure atomic msync. Before you do, it is very wise to check your invariants. And if this assertion fails, no problem. That's not going to affect the backing file at all. It is as though none of this code here ever happened. Okay, so there have been at least 6 implementations of failure atomic msync. I've worked on 4 or 5 of them. The first was sort of deeply baked into this monolithic, fault-tolerant distributed computing platform called Ken. It's just a user space library. The problem with that was that, well, it's difficult to disentangle the failure atomic msync aspect of it. That difficulty inspired my colleagues and I to implement a prototype in the Linux kernel. This is sort of like a clean, classic implementation of failure atomic msync in the kernel. That inspired our colleagues, I was working at HP Labs at the time, that inspired our colleagues in the HP storage division to implement a generalization of failure atomic msync in the HP advanced file system. This is a production file system that has been shipping with this enhancement to paying customers in appliance-like storage products since 2015. Independently of my colleagues and I at HP Labs, a group of academics at UC San Diego implemented failure atomic msync in the Nova file system. With the exception of the advanced file system, these early implementations were research prototypes. Okay? Currently, I'm aware of 3 relatively recent implementations of failure atomic msync. One is called famous, failure atomic msync in userspace. That's available since a few months now. You can grab it from the internet. It's described in the current issue of ACMQ. There's a variation of famous that is based on file system snapshotting. Christoph told me how to implement failure atomic msync with like 24 lines of code. And I'll show you the important 12 lines of those code later. So implementing failure atomic msync need not be difficult if you just do what Christoph says. Now, not to be outdone, Christoph himself is implementing failure atomic msync in the XFS file system. In the long term, I expect that an implementation like that, a file system implementation, will turn out to be the best mode of implementation for failure atomic msync if we're implementing on conventional hardware, okay? The point of this slide is that the abstraction, the interface of failure atomic msync admits a wide range of implementations. You can implement it in user space, in a file system, in the OS kernel. We've done each at least once. Several of the implementation styles have been done 2 or 3 times. The first 3 implementations that I worked on were extensively tested against whole system power interruptions. We set some system running using failure atomic msync to protect the integrity of data while it's being continuously updated, and then we yank power on the whole machine, at least a few hundred times. Here's, forgive me while I administer a brief sermon. You have to do this, right? If you're designing any contraption that claims to tolerate power outages, you must test against that. That's not the only kind of test you have to run. It's not sufficient, but it is necessary. Okay, so we have a lot of experience applying failure atomic msync in applications. The first 2 bullet points here are essentially similar. There's a networked key value store called Tycoon, and there's an embedded SQL database called SQLite that both have a curious property. Both of these have crash-resilient transactional modes of operation, but each also has a non-crash-resilient mode of operation that's intended to be faster. And it so happens that the non-crash-resilient modes of operation of Tycoon and of SQLite lay out all their data structures in memory-mapped files. So in some sense, they're written in what I previously called the persistent memory style of programming, right? But they use conventional mmap and msync, so they're not crash-resilient. Well, guess what? It takes 1 or 2 lines of code to slide failure atomic msync underneath the non-crash resilient modes of operation in Tycoon and in SQLite and transform them into crash resilient modes of operation. Oh, and by the way, they're faster than the native transaction mechanisms in both cases. Another interesting story involves a team of academics led by a member of the JavaScript Language Standards Committee. They prototyped a crash-resilient JavaScript interpreter based on Google's V8. It took one developer working with encouragement and support from Google a couple of months to transform the V8 JavaScript interpreter into a crash-resilient JavaScript interpreter. JavaScript is really an interesting place to do something like that because the language has a natural event-driven flavor. And basically what the developer here did was he made every iteration of the event loop a transaction. Okay? Biggest success story we've had with failure atomic msync involves HP Indigo printing presses. An Indigo press is a high-volume, high-quality printing press. It can fill a room, it can cost $1 million, and they had a problem. The mom-and-pop print shops that these things operate in had experienced power failures surprisingly often. When an Indigo press went down due to a power failure, the power might come back on in a few minutes, but the press was down for hours or days because the crash caused corruption in the print workflow control software. A single developer working for 2 or 3 weeks was able to slide a user space implementation of failure atomic msync underneath the complex, highly performance-tuned software controlling HP Indigo presses and make it crash resilient. The Indigo people had previously tried more than once to retrofit crash resilience onto their software, but it was too hard. The software was too complex. Failure atomic msync is a nice abstraction because all you have to do is make sure you put your data structures in it, call msync at the right time. The net effect was that recovery times following crashes decreased from hours or days to about 6 minutes. Failure atomic msync makes it easy to retrofit crash resilience onto software that was never intended to be crash resilient. There are some other nice properties of failure atomic msync. The durability technology that you use in the storage layer is completely unrestricted. You can use an individual storage device like a hard disk, a SSD, a local RAID array, highly available, multiply replicated, strongly durable cloud storage, et cetera, that's entirely up to you. Those who configure and run the storage system get to make whatever trade-offs they want among monetary cost and other factors like the strength of durability, the extent of availability, performance. The application logic doesn't change at all. Some implementations of failure atomic msync are very big data friendly, right? So for example, a user space implementation that ultimately is keeping persistent data in files can handle persistent data as big as a file. How big is that? You get to decide. The maximum size of the working set when you're manipulating persistent data in a file is bounded only by the size of virtual memory on the computer that you're using. And the, loosely speaking, transaction size, the amount of data that changes between one call of msync and the next is limited only by the amount of free storage. Now, some implementations of failure atomic msync give you data versioning for free. Every time you call msync, you're creating a version of your data to which you can revert later if you want. It's easy for programmers to reason about failure atomic msync because it doesn't create new behaviors, it just takes away bad old behaviors from conventional mmap and msync. And finally, the programmer doesn't have to pair up begin transaction, end transaction calls. Everything between consecutive msync calls is a durability transaction. And that's good news because history has shown that when you force programmers to pair up calls like malloc and free and lock and unlock, open and close, programmers often get it wrong. You can't get that wrong with failure atomic msync. Now, I mentioned this earlier, failure atomic msync in user space, or FAMOUS, is a library that I wrote recently. It's very simple, it's a couple hundred lines of code. It tracks modifications to the in-memory image by using a Linux feature called soft dirty bits. That's why FAMOUS only runs on Linux. uses a very simple undo logging scheme to atomically update the backing file. There are a couple of optimizations that reduce the size of logs in certain common scenarios. Famous gives you data versioning for free. All you have to do is keep around the undo logs that are created every time you call msync, and you can use them to revert your backing file to previous versions. I released Famous earlier this summer. Some of the details about it are available in that ACMQ article in the current issue. I have not yet subjected Famous to power fail tests, so you have been warned. Unlike the other earlier implementations of failure atomic msync that I worked on, haven't done this yet. Oh, and it's not heavily performance tuned. Now, there's a variation of Famous called Famous Snap that has mostly the same goals, but it's based on an idea that Christoph suggested a couple months ago. It leverages efficient reflink-based file snapshots in certain file systems, including ButterFS, XFS, OCFS2. So it only runs on one of those file systems. The interface of Famous Snap is not as clean as classic failure atomic msync or as the interface to Famous, which is a problem. Before the end of the year, I intend to release this and publish it. Now, the essence of Famous Snap is about a dozen lines of code, which I'm showing here. The implementation contains another dozen lines of code that are less interesting than this. Again, implementing failure atomic msync in user space can be a couple of dozen lines of code if you listen to Christoph. In the future, one of my top priorities now is to subject both Famous and Famous Snap to extensive whole system power interruption tests to make sure that they really do protect the integrity of persistent data from corruption by crashes. Some other things I wish other people would do that would make it easier to implement failure atomic msync in user space. There's a Windows interface called GetWriteWatch that is much cleaner and nicer than other ways of tracking memory modifications that are currently available on Linux. The Linux alternatives that I'm aware of include catching sig-seg-vs. I've done that. That's what Ken did. Using soft dirty bits. I've done that. That's what Famous does. User fault FD. I haven't worked up the courage to do that yet. GetWriteWatch, the Windows interface, in my view, is cleaner than all those. Furthermore, I think it would be lovely if we had stronger semantics for mmap on file-backed memory mappings. That's not the way. mlock currently doesn't do what I want when applied to file-backed memory mappings, but I see no reason why it couldn't. Because it is often very convenient to design persistent data structures that must be mapped at the same virtual addresses every time, it would be really nice if we had an understanding, a widespread understanding that a certain region of our 64-bit address space is going to be the last place that linkers and loaders and conventional memory allocators and everything else goes when it needs empty address space. That will allow applications to get there first and map persistent data in. I think it would do no harm and it would do much good if we had some sort of a standardized understanding that there is a region of the address space that is for applications to do things like map fixed data structures. Finally, I wish GCC and other open source compilers would steal another idea from Microsoft. Visual Studio contains support for what are called based pointers. The rationale for based pointers is precisely to support relocatable data structures laid out in memory mapped files. I wish we had that in something like GCC. Finally, I wish I could tell my compiler to coerce page alignment for data structures. Tell it to align some structure or array on a 4K boundary or a 2 meg boundary or a 1 gig boundary.
You can't actually do the attribute aligned in GCC.
Yeah, but what the largest value of that, I don't think GCC promises to honor. For instance, if you use that attribute to say, I want this aligned on a 1 gigabyte boundary, I don't think it feels bound to do that.
I'm not sure what the max value is, but at least for the small ones, like a page size, it actually is.
Okay, well that's new. I learn something new every day from you, Krista. Well, that's progress. If you can do this on a 4K page, that's good news. Okay, so wrapping up, I've talked today about persistent memory as a purely software abstraction and a corresponding style of programming that offers many of the same benefits as the style of programming that NVM naturally invites, but it can be implemented and practiced on conventional hardware. If you're worried about failures, failure atomic msync is a mechanism that prevents failures from corrupting your persistent data, and there are many ways of implementing that. Famous and Famous Snap are user space implementations of failure atomic msync. One has been released recently, one is imminent, and I have this article in the current issue of ACMQ that talks about persistent memory programming on conventional hardware, gives you some details about Famous. Now I'm happy to take your questions.
I'll ask the ugly one.
Sure.
Is there a 6-step how Famous actually pulls this off?
Well, the source code is that you can read the source.
I can go read it, but is there a simple flowchart?
Yes.
Game that you play?
Yeah. Right. So there are basically two problems that every implementation of failure atomic msync must address. You need to make sure that the backing file is only modified when msync is called, or when the equivalent of msync is called, right? And when msync is called, you have to figure out what pages in memory have been modified since the last time you called msync, and make those changes to the backing file atomically in the face of failure, right? Famous uses undo logging. So what it does is, let me see if I can remember this. I use soft dirty bits to find out what 4K pages of memory have changed since the last time I called the moral equivalent of msync, okay? I go to the backing file and I take the pristine versions of those pages. I put them in an undo log. Then I write the dirty or the modified pages from the in-memory image down in place to the backing file. If I crash during that process, I have to use the undo log to revert the state of the backing file to what it was before I began. Right? If all goes well, if I succeed in writing to the backing file all of the modified pages of the in-memory image, well then, I'm done. I don't need the undo log anymore. I can keep it around if I later decide I want to roll back the state of the backing file. I can still use it to revert. But does that, have I addressed your question?
And the pages can be the number you want it to be.
Well, pages are 4K in size because I'm using hardware features that are exposed through an interface called soft dirty bits to understand which pages of memory have been modified since the last time I made the moral equivalent of msync call. We can get we can get a piece of paper and I can show you.
Yeah, that was enough.
Okay. Do you believe it? I mean,
yeah,
okay.
Absolutely.
Did anybody actually download it and actually run the code? Nobody?
You sent it to me.
What?
I know that was you.
I offered a prize, people. You
You skipped the first part about preventing partial rights before the call.
I'm sorry?
You skipped the first part about how you implemented preventing partial rights before you make this the call.
Partial rights meaning?
Preventing updates to the backing store before you.
Well, so different implementations address that problem in different ways. So Famous, the user space implementation, the only way the backing file is ever modified is through through a library call. It's a private mapping. It's not map shared. It's map private.
I think that was the answer.
Yeah. Yeah. So when Famous maps the backing file, it's a map private mapping. It's not map shared. My library goes around the map privateness to modify the backing file from the in-memory image. The OS doesn't do that for me. I'm doing that myself. Sorry if I omitted that. Is that clearer? Okay. Yep.
How do you prove you've done enough power or crashes testing wise?
I'm sorry?
How do you know that you've done enough crash testing to know that it's working with
The tests end when you become exhausted. So the testing cannot prove a program to be correct. It can only prove a program to be incorrect. Right? So what we did in the past with a user space implementation, the one that went into Indigo digital printing presses, a kernel implementation, and a file system implementation in the HP Advanced File System was we set up systems that were using failure atomic msync as the integrity protection mechanism of some software that's updating data. And we designed that software in such a way that corruption is easy to detect. Then we repeatedly, as in hundreds of times or more, physically disconnected power using a big relay, physically disconnected power from the system under test, restored power, checked the integrity of our data. Is the testing thorough enough? Testing is never thorough enough, right? So there are other testing techniques that I haven't mentioned that we've also used, like raising a sigabort between every pair of semicolons in the code, right? That it stresses things differently, right? We can inject kernel panics through a magic interface in the proc file system, right? You shout the wrong bad word in the right proc file, and it just panics the kernel immediately. We do tests like that too. Right? So, but crash injection testing is, I would say it's necessary but not sufficient. The thing I like about the 24 lines of code that Christoph inspired is you can stare at it and you can try to reason about it. How hard? I mean, 24 lines of code actually is a place for bugs to hide, but not that many. Yep.
I'm curious about the definition of persistence in this context. So, for example. Let's imagine two scenarios. One where you have a storage class memory on your channel and you have DRAM. So clearly it's not considered persistent until it's flushed out to the storage class memory.
Right. Here.
In a second scenario, now you have something like an NVM-N or an NRAM or an NVRAM technology where it's persistent, but it's also in the paging environment.
So I'm going to have to refer you to the title of my talk. I'm talking about programming on conventional hardware, right? Other people, many of whom are present, other people have done a lot of really cool work on how do you program novel, non-volatile memory hardware.
Oh, so NVM-N is not conventional hardware? In that context?
In the sense that I would refer to that for, the terminology, I hope I'm not using it too imprecisely. If you've got, for instance, an NVDIMM, right, I would call that non-volatile memory. I would call that a special kind of hardware, right? So that's not what motivated me to do this work, right? What motivated me to do this work is my laptop. DRAM plus some sort of block storage device. Now, if your block storage device is some new and improved model with 3D crosspoint inside, well, then I would expect things to get faster. But it's still a block storage device. Right? Okay, on that, I think I'm being kicked out. Okay. Thank you.